I think we need to discuss a more detail about the scalar and vector potential. What do you think? All of you clear about the scalar and vector potential? I want to know your opinions because I want to discuss this in more great detail.
Yes, sir.
Okay. So let me do that because this is a unique thing, and I saw your answer script, and I saw many students they wrote in tensor notations. So which is this is a very simple thing, but we should not do that. So if you don't understand, let me ask repeatedly. Don't worry about that. So I'll do it. Okay. So this is scalar and vector potential, and after that we will go to the radiation chapter. Okay. Basically the electromagnetic radiations. Okay. So first of all, today we'll do this potential formulation. Then we'll go for this radiation. So let me write down the Maxwell's equations first. So let me do this. This one, this side. Okay. So first of all, let me write the Maxwell's equations. Maxwell's equations tells that the first equation is del dot E is basically rho by epsilon 0. Then we have del cross E is basically you have minus dB by dt. Then we have del dot B is equal to 0. Then we have del cross B is equal to mu 0 J plus epsilon 0 mu 0 dE by dt. Here electric field is basically a vector. So you have electric field. This is basically a vector. So you have a Ex component, then you have a Y component, and you have a Z component. So this is a three-dimensional vector. Similarly, for the magnetic field, I can write B as Vx I cap plus Vy j cap plus Bz k cap. So this means I have three unknown quantities like Ex, Ey, Ez. And here there are three unknowns, that is three unknowns, that is Bx, By, Bz. So the main purpose of any electromagnetic problem is, so main the aim of Maxwell equation is to find E and B for a given rho and j. So this is rho and j is our source, and E V our effect or fields. Anyone would like to ask anything?
No, sir.
Okay, so the main purpose is, suppose we have a charge distribution, we need to calculate electric field or magnetic field. If the charge is varying, then it can create also magnetic field, and if we have a current that is also varying, that can also create electric field and magnetic field. So this is our source. This is very important. So the main aim of Maxwell's equation is, if you know the rho and j, or if you know this parameters, that is dB by dt, or if you know dE by dt, So there are 4 types of source of electricity and magnetism. If you know this, you can calculate E and B, right? Now let's examine one of these equations. Let's examine equation 2, right? So let me put this is 1, this is 2, this is 3, this is 4. Okay, so let's examine equation 2. Okay, so let's discuss Maxwell's equation 2. Let me delete it here. So this is important. So del dot B is equal to 0. Okay, let me write something here. Here B is basically magnetic field vector. What is its unit? Unit is Tesla. Tesla means 1 Newton divided by 1 meter per second into 1 coulomb. Okay, and it has 3 components. So I have discussed about this: Bx I cap, then By j cap plus Bz k cap. Right? So this is basically a vector notation. Del dot B is equal to 0. What I'm saying that divergence of this magnetic field vector is 0. So what does this mean? This means that if it means basically there are no source of magnetic field. Okay, there are basically no monopoles of magnetic field. Okay, so now I'm going to apply a vector law here. That vector law is for any vector, right? So curl of no, this is, I'll apply a different one. So div of curl of A is 0. This is valid for any vector A. Please understand this. Okay, so I can also write del dot curl of A dash. This is also 0. What does this mean? That if I write del dot B, del dot B is equal to 0, that implies del dot del cross any vector is basically 0. Okay, and I can also equate. So B is equal to del cross A. So I would like to highlight that this vector A is vector potential, and it is not unique. What does this mean? It is not unique means I can have another A dash which also can create the same B, because you can see this two relation. This is divergence of curl A is 0, divergence of curl A dash is 0, because this is general and it is valid for any vector. Okay, so this has to be very clear. Okay, so did you understand what is the meaning of not unique? That means any vector can create that same magnetic field. That means I'm writing it here. So A and A dash creates same. Is it clear? Yes, sir. Okay, so try to understand that we can have many vector potentials that creates the same magnetic field. That's why I am calling it, it is not a unique. Okay, that is basically the basis of gauge transformation. We'll discuss that more detail. Okay, so now next thing is here in electrostatic. So next discussion is in electrostatic. In electrostatic, del cross E is equal to 0 because E is conservative. Okay, and now I can express E Now I can express E as a gradient of some scalar function, okay, negative gradient. So that means negative gradient of scalar function V. Okay, but because this E in Maxwell's equation, this E in Maxwell's equation is not conservative anymore because it is an electrodynamic field. It is not, it is a electrodynamic field. It is a dynamic field, I'll write, because it can change. It is a dynamic field. That's why del cross E is not zero. Okay. So in Faraday law, del cross E is minus dB by dt. That means E is not zero. E is not, del cross E is not zero, means E is not conservative. Because it is not zero. Previously it was zero. Okay, that's why it was conservative. Now it is not conservative. So what we can do is that we are going to apply the above equation 1. This is our equation 1 in case of this one. So here what I'm going to apply, del cross E is now minus d by dt of del cross A. Okay. Next, let me do that. Here, del is basically signifies d by dx, and t is time. And this is position. And they are independent. Okay. So you can interchange now. So del cross E is now del outside minus I put dA by dt del cross. Let me dA by dt. I can, yes, I can do this one. I can do this one. I can directly do this one. Del cross E plus dA by dt bracket is equal to 0. Okay. Now this term is basically electric field, and its curl basically vanishes. That means E plus dA by dt, this vector is conservative because it is 0. Now I can express this conservative vector as a gradient, negative gradient of some scalar function. So this is called scalar potential. So let me write electric field. So now electric field is gradient of potential minus dA by dt. Okay, so this is electric field, and other one is the magnetic field. Magnetic field is B is equal to del cross A, and electric field is minus gradient of V minus dA by dt. Now I would like to write that here if A and V are known implies V and E can be calculated. Previously in Maxwell's equation, the Maxwell equation rho J known and B E calculated. So the main basic thing is in Maxwell's equation we have 4 equations but we have 6 unknowns. Okay, that's why it was difficult to calculate, but now we have reduced that problem. This is basically 3 component and this is basically 1 component. We have basically reduced the components from 6 to 4, and this is the way we basically calculate the electric field and magnetic field. And this A and B are called scalar potential and they are not unique. Okay, so I'll write this is very important. Okay, A and B are not unique. This is very important. All of you clear about this point?
Yes, sir.
Okay, so this is very important that you can create the same electric field, same magnetic field with different potentials. Like you can have A, V one set, and you can go to another set A dash, V dash with same E and B. So this is called Gauge transformation. This is called Gauge transformation. That means going from one system, going from one coordinate to other coordinate. Okay, so you have old potential. So this is old potential. This is new potential. So what I would like to say here is that because A and B are not unique, you can have another set of A dash B dash with same electric field, magnetic field by this equations, by this B, this is the equation, this is the 1, this is the 2. If you know A and B, you can create the electric field and magnetic field. Another set is that because A and B are not unique, you can have the same electric field, magnetic field, another A dash B dash. Okay, so this transformation from old potentials to new potentials keeping same E and B is called the Gauge transformation. This is the basic very meaning of Gauge transformation. That means I'm writing it here, Gauge transformation. So I'll write it GT. GT allows us to go from old A B potential to new A dash B dash potential by keeping E and B same. Okay, so this is the basic thing. Now we'll see what is the relation to find relation between A to A dash and B to B dash. Did you understand the Gauss transformation basics? That is important. We are having old coordinates, we go to a new coordinates, but we keep the electric field, magnetic field constant. So that is called the Gauss transformation. Is it clear?
Yes, sir.
Okay. So let me go to the next way how we should do this. Okay. So now, see, in any problem, the main objective is to find the electric field and magnetic field. Either you have the source charges or you have the potentials. Okay. So let me do that first. So relation, yeah. So let me have A dash as A plus alpha. Okay. And V dash V plus beta. They have the same units. Alpha has the same unit of A and beta has the same unit of B. Okay. So now I would like to write that both the calls they will give the same equal, right? Sorry. We know that del cross A dash is basically B. Del cross A is also B. They will give rise to the same magnetic field. That means this implies del cross alpha is equal to 0. Is it clear or not? I'll do that
Yes,
again. I think let me do that in a better way because these potentials are very, very important. Okay. So let me apply that. So let me apply. Let me take a curl of this equation. Del cross A dash is equal to del cross A plus del cross alpha. That implies this will give the same magnetic field. This will give the same magnetic field plus del cross alpha. That implies del cross alpha is equal to 0. This is a very important concept. Now alpha is conservative because it is del cross alpha is 0. What I can do with conservative, if something is conservative, I can represent that some gradient of some scalar function. Okay, let that be lambda. Okay, lambda is a scalar function. Is it clear up to this point?
yes, sir.
Okay, now next thing is we know the same thing. Two potential will also give rise to the same electric field, right? So let me take the gradient. So this is V dash. So V dash is basically V plus alpha. So gradient of V dash is equal to gradient of V plus gradient of alpha. So this is E, right? So this is E. So this is E plus this is the same. So del dot V is basically how much? V is is dA by dt. Alpha d beta by dt. Okay. So now this is alpha is a scalar function. Alpha is a vector. This is alpha. This is beta. So E is basically we have the expressions for E. E is basically grad of V minus, this is basically E minus dA by dt. This is the reference equation. Okay, so you can take a negative, so this side will be positive. Okay, so here we are adding this potential B here, right? So this is grad of B plus, here we have made an addition. This is alpha in the vector. So this one d alpha is a vector by dt is equal to 0. Now this curl is basically the electric field. So this is 0. So we can have beta. Beta is del cross B alpha gradient. So next del cross B plus alpha, how much you calculate? Grad of lambda. D grad of lambda divided by d. This is equal to 0. Alpha is equal to grad of lambda. So this is grad of B plus d lambda by dt is equal to 0. Property of gradient then implies B plus d lambda by dt now is equal some scalar position. So grad of f is 0. So this is some grad of 0. So this is some scalar function. So some scalar is some scalar function. Some scalar. I'll write that as some kb, right? Yeah, k of t. Some scalar. So beta is equal to minus d lambda by dt plus k of t, and kt is absorbed to lambda because they are functions of t. So beta is equal to minus d lambda by dt. And now I can write the final expression. So if a dash is equal to a plus grad of lambda, and this is v is equal to v minus d lambda by dt. D lambda by dt. This is gauge
V dash.
transform. Yes, tell me.
The V dash.
V dash. Sorry, V dash. Yeah. So it is saying that. What actually physically it signifies that if the old, this is old, right? This is old. This is new. So if I want to go from old coordinates to the new coordinates, keeping E and B constant, suppose I will do the Gauss transformation. It means I'll go from old coordinate to the new coordinate, provided the condition is that I have to add a gradient of scalar function to the old coordinate. The same thing and I'll subtract the potential. So this is A is vector potential. A is vector and V is basically scalar. So when I go from A dash to A, right? So whenever I go from A to A dash, what I'll do, I'll add any scalar function, suppose lambda, to that vector. So it will give me new, but condition is that I have to minus this d lambda by dt from the same potential. Then only it will give me the new scalar potential, and it will keep E and B constant. Is it clear?
Yes.
Is it clear? So the way of doing this Gauss transformation is, if you have a scalar function lambda, you add them to the old coordinates, it will give you the new vector potential, but you have to also take a negative of that scalar potential, means with respect to time, in the scalar potential, which is basically give you the electric field. Okay, so this condition, how much you add here, you have to subtract this amount d lambda by dt from the potential. This is called the Gauss transformation. This is happening because and only because these potentials are not unique. So it is better to handle them, right? It is, if they are not unique, you can make an arbitrary choice, because this is happening because A and B are not unique. So if they are not unique, you can choose them up to your choice. Okay, own choice. Okay, so what you can do here, there are two type of transformation. One is called Coulomb gauge transformation, and second is Lorentz gauge. In Coulomb gauge, what we do, we basically take del dot A is 0. We can choose a scalar potential such that del dot A will be 0, and here what we choose, del dot A is equal to minus epsilon 0 mu 0 dV by dt. So this is up to our choice how we choose the scalar and vector potentials. Okay, so these are our choices, because A are not unique, so we can make them such that this is del dot A is equal to 0. So these are the two transformations used in classical electrodynamics. Is it clear?
Can you repeat that alpha part?
Okay, you want to go for
How-
that alpha. Okay,
how
okay,
that
okay,
alpha came into role?
okay, okay. This part is clear.
Yes.
So I'll go from the beginning. So here del cross A dash, this is there. So this gives rise to the same magnetic field. So this is del cross alpha is equal to 0. So alpha is 0 means alpha is a vector. So this is a conservative one. So we can express a conservative vector to the gradient of scalar function. Always remember this thing, I'm writing it here. If, note, I write it, note, if del cross A, I'll write del cross C. Del cross C is 0, that means EC is conservative, and C can be expressed as gradient negative of some scalar function potential, like gravitational potential, whichever you like. Okay, so this is basically very important. Did you understand this concept first or not? Okay, now I'm going back to the step. Okay, so this is done. So what I did, del cross alpha is equal to 0. So I converted alpha to some scalar function gradient. I can take negative, positive, but depending upon my choice. It is not a big issue. Okay, that positive, negative is up to my choice. Okay, because it will be arbitrary vector. Okay, so this scalar lambda is an arbitrary scalar function, so I can change it. So alpha is equal to gradient of lambda. Is it clear? So similarly, what I did here, we know that electric field is of the form gradient of U plus dA by dt. We already derived this, I think here. Here. Do you remember this? This thing we have already derived, right? So here E is basically electric field, dA by dt is basically the potential, right? So what I have done here, here B is basically the potential, right? here B is basically the potential scalar function. So I expressed this gradient of B as this is basically the electric field. This is basically the electric field because B is a scalar function. I converted to the gradient of a scalar function that will give me electric field plus d alpha by dt. D alpha by dt because this is where is that gone? Right. I'll keep it here. You can see. Let me delete this. I'll. So E. What is the expression for E we got? E is basically negative gradient of a scalar function minus dA by dt. That means I can write negative of electric field. These negatives are not important right now. So I just write gradient of B plus dA by dt. Is it clear this line? So V is basically a scalar function. We have added that scalar function here, right? So this can create the electric field. So here I am writing gradient of B because this is the unit of electric field plus A. A is how much? This is basically a vector potential. What I have added to the vector potential? Alpha, right? So that's why I put it d alpha by dt. Okay, because this is conservative, because this has to be conservative because del gradient of B is not alone conservative because it is not an electrostatic field. So it has to be dynamic. So I have added d alpha by dt. That's what is 0. Is it okay? So I have put
Yes,
it. This is the same thing I have done it. See, the gradient of B is basically the electric field. D alpha by dt is basically the this is also the electric field because this is dA by dt form. This unit are same. So that's why it is a conservative one in electrodynamic. And next thing, alpha I have converted. This alpha is basically we have done it gradient of lambda. So I put gradient of lambda. Grad and d by dt are interchangeable. So I made an interchangeable this side. So gradient, this is like you take like, d by dx of a plus b. This is similar to that. This is not a big issue, right? So this is their gradient. So I added them in this format, property of the gradient. Then this is the gradient of 0. So this has to be a function of time. Okay, because this has to be a function of time because it is time variable is there. So this is lambda can be absorbed into k. Generally, you can put it as some scalar function. So I absorb k inside lambda. So kt can be absorbed to lambda. So in general, I can write beta is equal to d lambda by dt. Is it clear? See, something function is here. What I have done actually, c is a function of x, p is a function of x. So what I did, I observed this thing. I said this is a new c, but I don't want to change the notation, so it is just a new c, right? So it is just a lambda. Okay, they are the same function, so I observed into this only. Is it clear or not? See, these two are the same function of time, right? This is a function of time. This is a function of time. So I observe them inside. So this is like I can put the new lambda there. That doesn't matter. It is a scalar function. The main thing is when these are the two relations I would like to write. You always remember this. Curl of grad phi is equal to 0. Then div of curl A. This is equal to 0. This is basically valid for any phi. This is valid for any A. Is it clear? We are basically using these two properties of the vector analysis. Do you understand? So here I say conservative. Conservative always means curl of some vector is 0. That means this vector is basically I can write E is equal to grad of phi. This is very important notations. Okay, divergence, gradient, and curl. Okay, so let me take another Yeah. Now, how we will implement this transformations to the Maxwell's equation? That is the point. Okay. So let me put that. Let me do that first. Okay. So apply this potential. Now application of V and A to Maxwell's equation. So first thing is, let me write it clearly so that it is better. So my B is del cross A and my E is negative of gradient V minus dA by dt. We have the first Maxwell's equation. First Maxwell equation del dot E is equal to rho by epsilon 0. So what I'm going to do, I'm going to put this electric field there. So I'll put electric field there. So this is del dot negative gradient of V minus dA by dt is equal to rho by epsilon 0. Is it clear?
Yes, sir.
So I am rho by epsilon 0. So what I'm going to do here, so this is del square V minus d by dt of del d by dt del dot A is equal to rho by epsilon 0. So I'm writing del square V plus d by dt del dot A is equal to minus rho by epsilon 0. Next I'll put equation 10. Okay, so this is my first case. This is one. What do you see here is that if you know this is the source, then you can create V and A. Is it clear?
Yes, sir.
Similarly, I'll apply another equation, that is del cross E. Del cross E is equal to minus dB by dt. That implies del cross E is basically minus grad of V minus dA by dt is equal to minus d by dt of del cross E. Del cross E equation 10.2 to Give me 1 minute. Two, two, 23. Del cross B. Del cross B. Sorry, not this one. Del cross B is equal to minus, sorry, plus mu 0 J plus epsilon 0 mu 0 dE by dt. So this is del cross A is equal to mu 0 J plus epsilon 0 mu 0 d by dt of grad of V minus dA by dt. Is it clear?
Yes, sir.
So now I'm going to the next step. So if you add them, let me do that systematically. So this is basically del square A minus let me take it, write it, del gradient of A minus del square A is equal to mu 0 J plus epsilon 0 mu 0 epsilon 0 mu 0 gradient of this. I can do minus here directly. This is minus dV by dt minus epsilon 0 mu 0 d square A by dt square. Is it clear?
Yes, sir.
Okay. So next I'm writing del square A minus mu 0 epsilon 0 mu 0 epsilon 0 d square A by dt square minus gradient of del dot A, gradient of del dot A plus epsilon 0 mu 0 d V by dt by dt is equal to minus mu 0. Is it clear?
Yes, sir.
So I just interchanged both the things, right? So this side I put it this side I put it this side. Okay. So the main purpose is, this is basically your source, and this side, this complete, this is basically B and A effect. But the problem is, this is I put equations too. Now I'll ask one thing. This is my first equation. Okay. This is one. We know that source and we can calculate V and A. If we know the charge density. Here also, if we know the current density, we can calculate A and V. But the problem is, this 1 and 2 are ugly. Yes or no? These are very complicated equations. Do you agree with me or not?